Okay, so for the next section of the session, what we want to see is the generalization of the theta functions that we defined for elliptic curves. As we saw already in that case, these are series that are that converge very fast, so they are great for numerical computation purposes. And the goal would be to obtain some type of expression that allows us to go from the lattice of a given Jacobian to a model for the curve for which it is the Jacobian. So here we have the Riemann theta functions. So we we are going to generalize the theory of theta functions that we saw in the case of elliptic curves to higher dimension. To do so, we define the following. So the Riemann theta function is the the function theta that goes from the C to the G times Siegel's upper half space to the complex numbers given by the sum theta of Z omega is equal to the sum. And now we take, so in the dimension 1 case, we just took n in the integers. Now we will take n in Z to the G. And this is the exponential of pi I. Now we have to take transpose because we are working with vectors and matrices. So pi I, the transpose of n omega n, plus 2 pi I transpose of n times Z. So this is exactly what one would expect from looking at the definition of theta functions. Of course, proving things in this, it's a bit more tricky because we have matrices and vectors and everything becomes a bit more convoluted. But it is still a lambda quasi-periodic function for lambda equal omega Z to the G plus Z to the G. So it's lambda periodic with respect to the lattice that it's determined by the small period matrix omega, and the automorphism factor is E of Z omega A plus B equal the exponential minus pi I transpose of A omega A minus 2 pi I transpose of A Z. Can I fit it there? No, it's okay. Okay, So no surprises here, everything is following more or less the situation that we had in dimension 1. And the thing is that one can actually see that the zero locus of this function is very much related to the curve, for which omega is the period matrix of the Jacobian. And this is given by a theorem of Riemann that we call the Riemann's vanishing theorem. Let C be a curve over the complex numbers of genus G. Let Jac of C be its Jacobian with period matrix omega in Hg. By saying that it's the Jacobian with period matrix omega, I just mean that this Jacobian is isomorphic to the complex terms C to the G quotient. The lattice defined by omega. So we wrote that here, omega Z to the G plus Z to the G. So it's just so that I can save some notation and some words. This of course implies the choice of bases both on the holomorphic differentials and on the homology. But we encase all this knowledge in this one short sentence. And let alpha be an Abel-Jacobi map of C. Again, of course, this choice of an Abel-Jacobi map will depend also on the choice of the distinct point, the basis that we took for to obtain this period matrix omega, etc. So this theorem contains at the same time a definition. There is an element delta in the Jacobian, the Riemann constant. With respect to alpha, such that the function, the theta function when we fix the period matrix, so we will write that as theta, we leave the first variable free and fix the second one to be the period matrix associated to our Jacobian, vanishes at a certain point of the complex vector space, even only if there exists points q1 up to qg minus 1 in the curve that satisfy the equality z congruent with alpha of q1 up to q plus g minus 1 minus delta modulo the lattice defined by omega. So basically this is defining this object that, if we are familiar with, just tells us that the zero locus of the Riemann theta function associated to a period matrix omega is exactly the image by the Abel-Jacobi map of this symmetric group of G minus 1 copies of the curve. So in fact, one can prove that this delta is actually unique. This doesn't really follow from this theorem, but this delta is unique up to the choice of alpha. So if we fix the Abel-Jacobi map that we want to work with, then delta is exactly a known value. Let me write this. I will write it as the freedom is in the choice of the base point, because that's the freedom that we have when we define the Abel-Jacobi map. But in practice, it means that it only depends on the Abel-Jacobi map that we chose. And indeed, for kappa, a canonical divisor of C, so just the divisor associated to a holomorphic differential on the curve, we have that the Riemann constant satisfies that 2 times the Riemann constant is equal to the image, we should say congruent to the image of via the Abel-Jacobi map of this canonical divisor, again modulo the lattice that we are working on. So this is the first step to be able to move between the world of the curves and the world of the complex series of its Jacobian. And we will end this section by giving a theorem of Siegel that gives exactly a way of writing functions on the curve in terms of theta functions on the Jacobian in the lines of what we saw with Abel's theorem in dimension 1. In this case, because we have this translation factor coming from the Riemann constant, and because we are in higher dimension, so the things are a bit more complicated, we will see. We have some more technical conditions, and that's what makes this result not entirely practical in like when we want to actually use it to create an algorithm. If there's enough time in the next session, we will see how one can use it to create this algorithm, at least for certain families of curves. But I'm getting ahead of myself. Let me first give these theorems. Whoops. Give me a second. So let me write what I was saying. The following. Theorem of Siegel links functions over C, well, on C actually, with quotients of Riemann theta functions in a manner or in a way similar to what we saw with Abel, theorem of Abel in in elliptic curves. And so first we need to define a technical concept that I'm just giving for the sake of completion, but it's not really relevant for understanding the idea of Siegel's theorem. So we say that an effective divisor D of degree G is special if there exists a regular differential omega with the divisor associated to omega being bigger or equal than D, and otherwise we call it non-special. I don't want to dwell much in this definition. I'm just giving it for sake of completeness, because I will actually use non-special divisors in the theorem that we are going for. So I will give this theorem a bit like a black box, but if you're interested in like the story behind it or how one can deduce it with what we have learned about Jacobians, I will pop some references so that you can dig a bit deeper and understand the geometry and the reasoning behind obtaining this final result. So, as before, let C be a curve of genus G over the complex numbers. And now take phi to be a function on our curve with a certain divisor. So we can compute the divisor of this, and it's degree zero divisor, that it's principal because it comes from a function, and we will write it as the sum from I1 to m of ai minus the sum from I equal 1 to m of vi. It's degree 0, so that's why m is the same on both sides. And ai and bi don't need to necessarily be distinct. They could be just the same point everywhere. Now let P in C be a distinct point. This will be the distinct point that we will choose for our Abel-Jacobi map. Let omega be the basis of the holomorphic differentials, for which we have that Jacobian is given by a certain period matrix, for which the Jacobian check C has, let me go to the other side, period matrix omega in the Siegel upper half space. Now let delta be the Riemann function, constant, Riemann constant with respect to the Abel-Jacobi map with base point P. So basically all this very long paragraph right now just means take all the notation in a very compatible way so that we can use everything that we've defined all this until now. And now we have the statement. So next we have to choose paths from the base point P to AI BI that satisfy that the sum for the integral from P to AI omega is equal to the sum of the integral from P to BI of omega. Here I goes from 1 till m in both sides. And this is actually a very tricky point of the theorem. What we are saying here is that we have chosen paths so that these sums are exactly the same. Here I'm not saying modulo de lattice. It's important because, as we have said several times, Riemann theta functions and theta functions also in the dimension 1 case are quasi-periodic, not periodic. So they are not well defined on the lattice, on the complex torus. We have to take representatives. And so it's important that when we take these representatives, we do it in a consistent manner so that everything that we end up claiming, it's all correct. So in this case, it's important that we take them so that this equality is satisfied. And so then, given an effective, non-special divisor D, which is the sum of G points of degree G that satisfies. And we have to take it so that the points in the effective divisor that we are choosing are not zeros or poles of the function that we chose. And now for the final result. And I'm gonna need the whole board for this one. And what we have is the following monstrous function or expression. We define the image by the function of the divisor to be just the product of the image of every point in the divisor. Keep in mind always what we saw in Abel's theorem for dimension 1. Here G would be 1, so we would just have the image of a point, would be whatever we write next. And this is E, a certain constant that does not depend on the divisor that we chose, times the product for J equal 1 up to M. Sorry, this is I from 1 to M, theta sum for J equal 1 up to G of the integral from P to Pj of omega minus the integral from P to AI omega minus the Riemann constant divided by J equal 1 to G integral P Pj omega minus P Bi omega minus delta omega. Where? And let me define the notation that it's new here. We have that E is an invertible, so a non-zero complex number that is independent of D. And the integrals from P to Pj take the same path both in the numerator and the denominator. Okay. So we have a monstrous equation that relates things that happen on the curve with things that happen on the complex torus, and I would encourage you to try to write down exactly this same statement in the case where g is equal to 1. You will find that we are actually writing exactly the same expression that we gave in the theorem of Abel in the case of elliptic curves, except that there we were talking about points in the lattice directly. Here we are looking at the points in the lattice via the Abel-Jacobi map. Okay, so we can discuss it on the platform, but basically we are choosing a function. If we, instead of writing it in terms of d, we just write it in terms of z, an element in c to the g, this would be theta at z minus the point that we have chosen as a 0, z minus the point we've chosen as a pole, and this delta that we have here, that it's this translate, would be equivalent to the reason why in that case we chose theta to be the theta function with characteristics 1/2, 1/2. And that's so that the zeros really align with the points that we are interested in the curve. Okay, so this is actually the result that we were looking for. The tricky part that we face when we are trying to use this is that here we are really talking about points of the curve and how they translate to the Jacobian. So if you know nothing about the curve, or you don't know the curve, it's kind of tricky to know what points of the Jacobian you have to use. But that is something that one can deal with case to case. There are cases in which the structure of the curve gives us enough information so that we can have an idea of what points to use. As I said before, if there's enough time on the last session of the course, we will see these applied to the case of genus 2, that, as you saw in the introductory session of the school, means that it's a hyperelliptic curve, so they have a pretty special structure that can be of use for this. And finally, for the sake of completeness, I will also introduce theta functions with characteristics in this general setting. We won't explicitly use them for now. Maybe we will do in the last session when we do the particular example for genus equal to 2. But I just want to introduce them because using characteristics instead of the elements of the complex vector space allows us to express in a more precise way when we are using points of entorsion on the lattice, as we saw when we did elliptic curves, where the barrier stress points of the curve correspond to the points with entries 1/2 on the characteristics. So let me write that. For completeness, let us also define the generalization of theta functions with characteristics So definition, the Riemann, I have the space, I think so. So as we did in the dimension one case, we take the characteristics to be x1, x2 with xi in R to the g. Here we have used a bit the notation. When we write x, we think of it as a vector of length 2g. When we write it as x1 and x2, we mean the first half and the second half, and we write it like this, even if this is a column and this is a row with 2 columns, etc., etc. It's a bit of an abuse of notation, but it's just more comfortable for the sake of writing. So the Riemann function with characteristic x is the function theta of x, has the same domain and codomain than the original one, given by, and well, I could write it here. Theta of x z omega equal to the sum for n in z to the g of the exponential of phi I the transpose of n plus x1 omega n plus x1 plus 2 pi I transposed of n plus x1 z plus x2. And as it happened in the dimension 1 case, this is just translation and multiplication by an exponential term of the original Riemann theta function, and it is lambda quasi-periodic for the period, for the lattice given by the period matrix omega. And it is also a modification of the Riemann theta function theta of x z omega is equal to, let me write more, start more to the left. Z plus omega x1 plus x2 omega. And as an exercise, it's a harder exercise than what we've seen so far. I invite you to rewrite Siegel's theorem in terms of theta functions with characteristics. This is interesting because if we choose the points P1, Pg on the divisor in the theorem to be torsion points, the integral of from the base point P to Pj of the holomorphic differentials will just have rational entries when written with respect to the lattice basis. And this is what we will use in the last session if there's time, when we look at the genus 2 case. The trickiest part of working with Riemann theta functions is working consistently with the representative of the points when we can think of them both in the complex vector space and the complex lattice. So be sure to pay special attention to the choices of representatives in those cases. And with this, I finish the session for today. Thank you.